Well, everybody, I wanted to run with you one example of how to do the thermodynamics problems. And you're going to have about 3 or 4 of these in your thermodynamics notes where you're watching the PowerPoint and then you're filling in the answers from the notes. But there's some problems in there that they give you examples for in the PowerPoint. But I wanted to run through the first one with you just to give you an example of it. So this is the first problem that comes up in 1.3.3, starting at step 18. They're telling you a 1 kilogram piece of aluminum metal at 90 degrees Celsius is placed in 4 liters or 4 kilograms of water at 25 degrees Celsius. Find the final temperature TF. Okay. Now, if you look at your PowerPoint, they start in slide 16 giving you some formulas. These formulas are also in your engineering formula sheet. The basic one here is energy transfer. The amount of energy transferred in joules is the mass in kilograms times what we call the specific heat capacity of the material, and that'll be given to you. And notice the units here. That kind of tells you what everything else needs to be in terms of. And then the change in temperature, delta T, that would be T final minus T initial. And that's represented by the Greek letter delta for change in temperature. Again, mass needs to be in kilograms. Temperature needs to be in Celsius. And that'll give you your amount of energy transfer in joules. Now, in slide 17, there's also additional variations of this formula where P is the rate of energy transfer, and that's whatever you get for Q divided by time, how much time elapsed while that energy was being transferred. That gives you the rate of energy transfer, which is watts, which is actually the joules per second. Okay, and then if you do some substitution in here with with both equations, there's another equation here that's giving you the rate of energy transfer based on a K value, which is thermal conductivity of the material, and that will be given to you, times the area that's being exposed to the heat, again, times the change in temperature, and times L. In this case, L represents the thickness of the material. We've used up all the T's, so we go to L for thickness, okay, or length, I guess you would say. And then they rearrange this formula to give you a way to calculate the thermal conductivity yourself. If you know all of these things, you can calculate T. So, and then starting in slide 18, they actually start giving you examples. And if you run through all of these examples a few times, you should figure out the process. But what I'm going to do is I'm going to go back to this formula here, and I'm going to Q equals MC delta T. And we're going to apply it to this first problem that's in 133, starting at step 18. And they do that engineering technique where they say list all known values, list all unknown values, list your equations, then apply the equations, and then solve. Okay, so we're going to follow that process here. So I'm going to show you my little ladybug camera here, and this is the problem that we just read right here, step 18. A 1 kilogram aluminum block at 90 degrees, really hot, now Celsius now, is placed in 4 kilograms of water. The water is at 25 degrees Celsius. So when you drop hot metal in cold water, it's going to sizzle, it's going to steam, and eventually the block and the water will be the same temperature. That's that heat transfer, thermodynamics, the movement of heat. It's eventually going to steady out somewhere between 25 and 90. It's going to be your final temperature of the water and the metal after it sets long enough. So I just rewrote all these formulas up here at the top that you just saw in slides 16 and 17. And then we're going to look here at the process, okay? So let's start out by, first of all, listing all of our known values. We know the mass of the aluminum is 1 kilogram. We know the mass of the water is 4 kilograms. We know the temperature of the aluminum is 90 degrees Celsius, and we know the temperature of the water is 25 degrees Celsius. So we're going to drop that hot metal in the water and make it sizzle, right? We are given here the C value, the heat coefficient value, the the specific heat capacity of aluminum and specific heat capacity of water. So there's those two numbers. They're given to you. You can find those in tables. What is unknown to us is the final temperature, and that's going to come from delta T. Like we're going to know the initial temperature, and we're going to have to calculate the delta T, and then from delta T and the initial temperature, we can calculate the final temperature. So it's kind of a two-step process. All right, so knowns and unknowns. That's all I've listed so far. All right, so let's look at a little bit of how we would approach this. Now, basically, this is the formula. This is the formula that I'm applying. Q equals MC delta T. We just saw that in the PowerPoint. Now, one thing that is maybe hidden in what you read, and this is the key to solving this. In any thermodynamics problem, whatever amount of energy is lost by one object is gained by the other. So the energy lost by the hot aluminum as it's cooling off, that heat energy is captured by the water. So whatever the metal loses, the water gains. But remember, water has a much higher specific heat capacity, so it takes a lot more energy to heat up water than it does to heat up aluminum. Okay, so it's not going to be a direct, the water's not going to turn 90 degrees. It's going to start getting hotter, but we got to find what that final temperature is. So we could either find the amount of heat generated or lost by the aluminum, or we could find the amount of heat gained by the water. It turns out we know everything we need to know about the aluminum. So we're gonna calculate the heat lost, the amount of heat energy lost by the aluminum, and that would equal the heat energy lost by the water, right? So MC delta T, the mass of the aluminum is 1 kilogram. I'm just substituting in the formula now. The specific heat capacity of aluminum is 900, and the delta T is 90 minus the final temperature. If I simplify all of this, I get 900 times 90 minus TF. Again, we don't know the final temperature yet because we know this 90 is going to cool down to some final temperature, but we don't know what it is yet, right? So if you use your distributive property, 900 times 90 gives you 81,000, and 900 times TF gives you 900 TF. And so that is the equation for the Q lost. Let's do the same thing for the water. MC delta T. The mass of the water is 4 kilograms. The specific heat capacity is 4184. And change in temperature is TF minus 25. Now, in this case, the TF is on the left because we know the final temperature is going to be hotter for the water. So that'll give us a positive number here. So TF minus 25 is the delta T for the water. Again, using your same process, multiply these outside together, then use your distributive property. You get an expression for the Q gained of 16,736 TF minus the 41,8400. Okay, so when you carry out these distributive property, you get this equal to this. Again, Q loss has to equal Q gain. That's the key. So you put the aluminum formula equal to the water formula, and then you start solving for TF. So I'm going to add 418,400 to both sides, and I'm going to subtract. I'm going to add 900 TF to both sides. So you end up with 499,400 equal 17636 TF. This is multiplication here. So then if I divide both sides by 17636, I get the final temperature is 28.3 degrees Celsius. So you notice that the aluminum started at 90 and the water started at 25. And even dropping that small chunk of aluminum in a bigger chunk of water only raised the water temperature about 3 degrees Celsius. So this is the process that you will go through for the other problems, the applications in 133. Again, go back and look at the PowerPoint examples, have your formulas next to you, Start by listing your unknowns, your knowns, and then your unknowns, and then the formulas, and then plug into the formulas, solve, and you should be able to come up with a final answer.